Oh,
Oh,
I
sorry.
checked it.
You didn't change it.
So we have some remote attendees, so that's why we put it in the room. They can actually see all of us also.
And that's the mic, so maybe I should stay in the front.
Yeah, sure.
That's fine.
No, I think this can move around.
Okay, super. Yeah, our goal is to provide computing resources to anybody in the world. So if you want to run on our systems, you don't have to be a US citizen or be located in the US. You can apply for an allocation. There are 3 ways to apply for an allocation. 3/5 of our entire allocation on the system is managed by a program called Insight, which is co-managed by Oak Ridge and us. Another part of it is managed by DOE, and it's called the ALCF allocation. And then we have a small allocation called Director's Discretionary, which is not to do science, but if you want to get started on our systems and get to know how to report and how to use it, you can do that with the goal of applying for science projects through either Insight or ALCF in the future. One thing about our computing resources, and especially our upcoming system, Aurora, we want to be able to support workloads in all 3 categories or 3 pillars. The traditional HPC, which is the simulation projects. Okay. The traditional HPC, and then data workloads which have heavy data use in them, or the deep learning workloads. Oh, now I have to use the right now. Okay. So the computing resources we have had since we got started in 2004, we started with the Blue Gene series. We had a single rack of Blue Gene L then. We did upgrade to the Blue Gene P and the Blue Gene Q, all from IBM. Currently, the systems, those are all have been decommissioned. The systems we have in production now that our users use is called Theta, which is a mini-core Knights Landing based system from Intel, and that's going to be decommissioned at the end of this year. And then we have Polaris, which is actually an AMD Milan plus NVIDIA A100 based system. And Aurora is the system we are all waiting for, which is the Exascale system. The big takeaway is that if you notice that both the IBM Blue Gene series and Theta are all CPU-based systems, homogeneous systems. Polaris was our first foray into heterogeneous GPU computing, and then Aurora will be an Intel GPU-based system. So these are the computing resources, and I talked about Theta and Polaris. Cooley is this cluster that we have, and let me see if I can do it. Cooley is this cluster we have. That's also getting long in the tooth. We might not upgrade that to a special WISC cluster because now that we have heterogeneous systems like Polaris and Aurora, people can use those GPUs there to do visualization too. The file systems that we have is cluster-based. We have 2 of them. It's called Grand and Eagle. Technology-wise, they are same. They are HPE clusters, so InfiniBand clusters. They're both about 100 petabytes, and their performance is about 650 gigabytes per second. The Grand is the file system all the projects uses, the allocations I talked about, Insight, ALCF, etc. Eagle is actually our first foray into having a community file system. So if you had an allocation for the computing resources and you generated data that you want to use in the future or be able to share with other people on Globus, you can use the Eagle community file system. And finally, a bit about this JLSC, which is on top. This is an experimental facility, JLSC, the acronym stands for Joint Laboratory for System Evaluation. We have a number of test beds there at a very small scale. This is basically people trying to understand the latest architectures, be it GPU, CPU, storage, whatever, and quantum computing and simulators, and play with them to understand performance with the hope of buying or collaborating with vendors in buying systems in the future. One other thing that is not mentioned, but it started recently is about a year and a half ago, is an exploration into AI testbed hardware. We have a number of users with science, traditional and scientific HPC computing that are now getting into having machine learning as part of their application. And there are a lot of accelerator-based hardware for these type of workloads. So we have these systems, and we used to have it in a special space called the AI testbed space, because they all had NDA and only Argonne users could use it. But now we are moving it into like Cerebrus, Sambanova, and GraphCore have already moved into the ALCF, Computing Resources Enclave, because the NDAs have been removed from them. So if you're interested in testing out these type of hardware, you can apply for a DD allocation and ask to use it. All right, so let's move on to Aurora, which is why we are here. This is a great, from a scheduling point of view, this is a great time to present on it because Intel removed a lot of NDA information and announced it on Monday. I had a colleague of mine talk in another BOF about Aurora application performance, and he couldn't share anything because it was all NDA. So the main takeaway, and I'll kind of dive deeper into all this in subsequent slides. The main takeaway is the peak performance is what Intel hasn't shared exact performance data for both the GPUs and the CPUs, but the main takeaway is that the system would have a peak performance of greater than 2 exaflops. It is an heterogeneous system with the first Intel discrete GPUs, which is called as the Intel Data Center GPU Max series. I had to look up to say it because we used to call it PVC, which was the code name. And the 4th generation of the Intel Xeon processors, and they call it Intel Xeon Max series, because it used to be codenamed Sapphire Rapids. And the difference between the Sapphire Rapids Q and the Max series is that it has high bandwidth memory on it. You might think like, why do you need high bandwidth memory? We do have data system, which is a many core architecture, KNL based, which has the MCD RAM, which is similar to the HBM. So many of our applications that have been running on these systems are very used to using high bandwidth memory. So they have ported it and optimized it for such an architecture. The compute node, there are 10,064 nodes, and each of these nodes have 2 SPRs and 6 PVCs on them, and there are 8 Slingshot NICs on them too. So you can do the math. There are about 64 of these nodes in each of the rack, comprising of 166 racks. So it's a huge footprint. And then what do I want to say? And the programming environment, I'll talk more about it as we go along. The storage, we can use the Lustre file systems I talked about previously, Eagle and Grand, but we also have something called Deus, which is an asynchronous object storage, and I'll talk more about it in subsequent slides. So how do you put these two together? There's kind of a high-level diagram, a cartoon picture. The compute blade, it's got 2 of these SPRs and 6 of the PVC GPUs. Each of these GPUs have 128 gigabytes of high bandwidth memory. The CPUs, the Sapphire Rapids, have 512 gigs of DDR5 and 128 gig. I'm sorry, that's a mistake. This should be 64. I'll correct that. 64 gigs of high bandwidth memory, or a total of 128 gigs amongst the 2 CPUs. The switch blade is Slingshot, and there are 32 of them in a rack and 64 of these nodes, and that makes up the entire system. What you see in red color are the PDUs. It's a water-cooled system. So a little more about the Aurora node. There is a Cartesian-ish picture on the right, and then you see the actual node onto your left. You can do the math. There are 6 GPUs, each with 128 gigs of HBM. The memory bandwidth numbers for these have also been released by Intel, and so I've included them and done the math. There are 8 NICs shown in green. These are Slingshot NICs. They are all PCI Gen 4. The PVCs and the SPR, the Xeon SPRs are all PCI Gen 5, and so you see a PCI switch that connects between those. You can actually move from data from the CPU memory to the NIC. You don't have to write back to the host processor memory to do that. So the host processor has both HBM, which is 64 gigs each on each of them, so a total of 128, and 512 gigs of DDR5 on each of them. And the number that Intel has released so far is that it's greater are equal to 130 teraflops, each of these nodes. The Xeon, I won't say much about it. It's the next generation chip Xeon. The cool thing about it is there are some optimization for AI acceleration, for confidential computing and all that. But the main takeaway is that these are special SKUs with high bandwidth memory on them. So the SBR SKUs without high bandwidth memory, they're available now. You can go get them from the Intel website. And so they might have more number of cores because some of the footprint is occupied by the high bandwidth memory on these. And the number of cores and the performance of this hasn't been made public yet. Intel GPUs, something that you might not know if you haven't been following them closely, is that Intel has been doing GPUs for a long time. For about 10 or 11 years, they were all integrated GPUs that you use for your displays. But the underlying architecture is the same. This is their first foray into discrete GPUs. They have different varieties of them, low powered ones, high performance ones, and what we call as the HPC ones, which is where Ponte Vecchio falls in. So that is that's a picture of a die from the Tiger Lake XC GPU on top. Ponte Vecchio, again, this is what Intel has released publicly, so I won't have any performance data. They did have one number of more than 52 teraflops when they released the data on Monday, but beware that the SKU in Aurora might be different from what their highest SKU is. It depends upon the TDP. So it is a very complex chip with more than 100 billion transistors. There are more than 47 active tiles, but there are at least 5 chiplets that are fused together, and these are different process node technology that they come from. So it's a very complex chip. Basics, the nitty-gritty about the PVC. If you're very familiar with the integrated GPUs, there is not much difference between the discrete GPUs and this. I'll share that with you. They have changed names. On the integrated GPUs, they used to call them as execution units or EUs. Now they have changed the name to XC cores, which have the vector engines and matrix engines on the far left. And you put the 16 of these XC cores together and you form a slice. And you put 4 of these slices together and 4 of the HBM memory controllers to form a stack, and you put 1 or 2 of these stacks together to form a tile, and multiple tiles form the actual PVC GPU. So the performance of your chip or the power TDP depends upon the number of XC cores you have in them. So, and Intel can turn on and turn off these XC cores, and they are all field replaceable. The turning on and turning off to control the performance and the power. All right, Aurora Fabric. I saw that there was a talk from Keith Underwood. It's Slingshot, and so I won't say much about it since Keith will be talking more about it, and I think he's going to do a roadmap too. It's Slingshot NICs and Slingshot switches, and this is what is Slingshot 11, and this is what is in many of the systems, like Polaris that we already have, like Frontier, like Perlmutter. It's a Dragonfly topology. The NICs used to be called Cassinis, and the switches used to be called Rosetta. They call it now the Slingshot switches and NICs. They have a number of features like quality of service, traffic classes, and very aggressive adaptive routing, multi-level congestion management, and things like that to get better performance. This is a picture of our 1D Dragonfly topology. So we have 166 racks on the compute side. So there are 166 groups. Each rack is a group. Inside the rack, the nodes are connected to the switches, and the switches are all, it has an all-to-all connection. All these are electrical, and the external global links are all optical. I haven't yet touched on this, but this is the DAO storage, the distributed asynchronous object store, which is the main storage on Aurora, but you see that it is tied to the Slingshot fabric. And what you see at the end are the gateway and service nodes. You see that each of these global links on the compute side, they are two links per arc, while what connects to Deos is all 8 links per arc. So there's quite a lot of bandwidth there. And what is on these connects to the service nodes are all 24 links to an arc. So much more bandwidth performance on that. And the total injection bandwidth, which is 8 MIGs, each of the total of 200 gigabytes per second, each one can do 25, and then you can multiply by the number of nodes to get the injection bandwidth, and the bisection bandwidth is 0.69 terabytes per second. Storage, I talked about the Lustre file systems that we have, which is the traditional file systems, which is Eagle and Grand. What we would have in Aurora is Deos. It is the main storage system, so if projects are using that, have their project files there, you don't have to move it to save it on the Lustre file systems. You can leave the data there, but if you have to move the data in between the Lustre file systems and this, it is not automatically done for you, but there are scripts to do that. So this is a picture of the Deos node. It shows the persistent memory DIMMs, and I think what it doesn't show is the SSDs inside. So this is this picture that we just saw. I just wanted to point out the higher bandwidth that you have with the 8 links to the arc between the Deos nodes, which are about 8 of them, and the total number of nodes is 1024, and the service node which has 24 links to an arc. There's another picture of the compute racks and the Deos racks. What you see with the blue paint covering, which is supposed to be Slingshot, are the compute racks here. So these red ones you see are the Deos nodes. So you can see they are all integrated into the Slingshot fabric. And the yellow ones are the gateway nodes. This is your traditional Lustre-based file systems, which is Eagle and Grand. And if you have to move data from the Deos nodes via the gateway nodes to the Lustre file system, you can do that. We provide scripts to do that. And these are the Deos nodes. They have, I think, 512 gigabytes of persistent memory, which is Optane, or the version next to that, and a couple of Samsung SSDs. Okay, so Intel also said that they have shipped to Argonne more than 10,000 nodes. The Argonne, the Aurora installation process is going on, and what you're seeing here, so we built a new data facility space to do this. There's about extra space, which is about 40,000 square foot, and it's got the mechanical rooms where all the plumbing and electrical substations are, and it also has a space where the public can view it. So when you do view, you'll see it from here. This is the space behind this is from where the public can view it. And what you would see is this picture or something like this. But if you stand between the racks, you see this. And the red and the blue tubing that you see there is for the water, the red for the hot water and the blue for the cold water. There's more than 44,000 gallons of water that is needed to keep this system going on the 166 racks. And what you see here is a picture of a separate system. It's a test and development system called Sunspot, and it's 2 racks. It's the same architecture as Aurora. There are 128 nodes, 64 nodes each, so a total of 128 nodes. You can do the math about the number of GPUs and Xeons. And this system is now being used, I think, we are in May. So from last November or so, it's been opened up for the Aurora early science projects and for the ECP projects. And so they are making use of that. And so the architecture is same as Aurora, as they are preparing their codes and things like that to run on Aurora. And once we open it up to users from those projects, they will move from Sunspot to Aurora. All right, very quickly on the software stack, I mentioned that we want to support all the 3 pillars, the traditional HPC, the data pillar, and the deep learning pillar. The big takeaway in this is that there are things that are very common to all the 3 types of applications or workloads, things like compilers, IO libraries, math libraries, and a scheduler and all that. But there are things that are special to each category. HPC languages, runtimes, directives, and things like that in the traditional simulation space using OpenMP and thing. And then things like in the learning space, you need frameworks and Python and data analysis library and all that. So all this work with Intel was done through the NRE collaboration. Intel, of course, building a discrete GPU for the first time, did not have all this in their software roadmap, but it was specially created the last few years. We have been collaborating with them. They call it One API. Basically, what One API provides you is like an open standard to develop this type of tools or libraries for different GPU architectures. What it provides you is a language, which is DPC++, optimized libraries like the math library, like OneDAL, the data analysis library, and a low-level API called L0 or level 0. And then they've used those to create different libraries and different tools. They have a base tool kit called One API, which gives you most of these components, including the performance tools and GDB debugger and all that. They have a drop-on to that called the HPC toolkit, which provides you the compilers and MKL and things like that. They have an AI toolkit, which provides you the OneDAL library, the OneDNN library, the communication library like OneCCL, and the frameworks like PyTorch and TensorFlow. And level zero is basically, the specs are out. It's a low-level API for managing the device memory, synchronization, command queue and command lists, and all that. So most of these have been ported to level 0, which is the low-level API. Programming models. How much time do we have?
We have 12 minutes.
12 minutes. Okay. Aurora programming models. We don't support CUDA. So it's our native programming language is called SYCL, or Intel calls it DPC++. And as they add features to DPC++, they try and push it to the open standard. It is open and it's a standard. It's been ported to it. SYCL was always working on the different types of CPUs. Now they have ported it to work on different GPUs too. Both NVIDIA and AMD GPU can run SYCL code, and I will say that because we have a contract with CodePlay where we have made it work on Frontier and Perlmutter and Polaris, which are NVIDIA GPUs. And I'll share some performance results too, showing SYCL performance on NVIDIA with applications compared to their native programming language, CUDA, programming model CUDA. We also have an experimental version of HIP. HIP is not an open standard, but it's open source. And there is an ECP project called HIP-LZ, where LZ stands for level 0, where we have ported HIP to make it available on Aurora. So if you have an application or a software library that runs with HIP on Frontier, you can run that on Aurora using this HIP-LZ. And hopefully Argonne is the one with the PI for the ECP project, and after ECP, we'll continue to support it. So not available is CUDA and OpenACC. So and what you're seeing, that pie chart on the right-hand side, we reached out to all the ESP projects that we run and to look what programming model they would be using on Aurora, and you can see most of them fall into or major portion of them fall into SYCL or OpenMP. And then the frameworks that was developed by the DoD labs like Raja and Opus that many applications use, those are also supported. They would use a SYCL backend on Aurora. What is SYCL? It's an C++ based abstraction layer. As I said, the version that Intel supports is DPC++. There are different implementations of SYCL. You have Compute CPP, Intel SYCL, TriSYCL, HIP-SYCL, and all that. What we liked about it was it was an open standard. We want something that was open and was a standard and not a proprietary language for the GPU. Okay, MPI. I have to talk about MPI because this is an ExaComm, but I'm not an expert on this. Aurora will support and be both the Cray MPI and the Intel MPI versions. They'll be MPI 3.0 compliant. And I mentioned about the NRE collaboration that we did on a number of these one API libraries and compilers and other tools. MPI was one of them. We did a lot of optimizations for MPI, and I've listed them. These are all being pushed to the open source community because Argonne wants the ability to download the MPitch version and be able to build it ourselves and make it available to our users. So nothing is proprietary here. Everything is pushed to the open source community. A number of optimizations we did was for the Intel GPU and support for multiple NICs on the node. One other thing, I think, Professor Panda, you might be aware of this. We have also modified the OSU benchmarks. That's what we use. And we have modified it to support level 0. And we have modified it to work with the Intel GPUs. The question is, I mean, Intel is ready to release it, but then somebody has to take the responsibility for maintaining it. That's something that you have to discuss with Intel, whether they would financially support it to get people to do that. So, but those are the benchmarks we use for acceptance to measure performance, the OSU benchmarks. And again, I mean, this is another list of different optimizations we have done through the MPI NRE. The last one, the collectives optimized for the Dragonfly network topology. Those, I think, that's the only thing that is left to push it to open source. We haven't done that yet because we have been able to test only on Sunspot, which is 2 racks. We want to make sure that things are working and it is benefiting performance on Aurora before we do that. So brief, very quickly about Aurora applications. We work closely with 2 projects. One is called the Aurora Yearly Science, that's run by the Argonne Leadership Facility, and of course the Exascale Computing Project, which you all might have heard of. There are on the ESP side, we have about 19 applications. 9 of them are the traditional HPC, 5 in data, and 5 in deep learning. And on the ECP side, there are several projects, both on the software side and the application side. But there are 21 application projects on the ECP side. We work very closely with 15 of them. We have points of contact, that is staff members who work closely with this, and their job is to test performance on Aurora. And when I talk about testing and porting, this is something we've been doing for 3 years. So what we have today is Sunspot, which has the Aurora node, which is at the right-hand side, almost extreme end. But we've been testing these on these integrated GPUs, which is called Iris when we first started. And there have been versions of the discrete GPUs that Intel hasn't productized, but have made available to us. They are all in this, what I called as the Joint Laboratory for System Evaluation, JLSC. If your organization, if you need access to them, you can use them. There are now PBC nodes there too. All you need is a CNDA between Intel and your thing. So the hardware is actually all PRQ, it's all released. What you need a CNDA for is to basically be able to access the software. Intel does all the intermediate ops of the one API that's not available to the public. So that's all NDA information that they don't want people to access until you sign a CNDA. So you have to sign a terms of use form too. This kind of tells you the effort that is going on. So with the test beds that I showed you, we've been tracking this since Q4 of 2000. What you see on the left, the bar charts that you see on the left is applications that have finished their science implementation. These people are developing their applications to work on an exascale machine to do science at a large scale. So they might have been adding new physics to their codes. So these are the projects that they were working on, and they were all very partial when it first started. Now they have almost completed them as we speak. And then what you see on the right is porting to an Aurora programming model, be it OpenMP, be it SYCL, and how the projects have made progress. And as they were doing it, what they were testing on was the early tests, the test beds that I showed in the previous slide. And this is the way we track. You see different versions of green. The number of applications doesn't coincide with the number of projects because certain projects could have multiple applications. But what you see is dark green is people who have been running on Sunspot and are very happy with their performance. It is where they expected it to be and happy with it. The lighter green would be like they're seeing only about 80% or 70% of performance. And similarly, the different flavors of green is that. The things that are yellow or brown or red would be things that that they have some problem that they have to work around. Could be a compiler issue, could be a library issue, MPI not scaling properly, and things like that that they're still debugging and working on. So this is something that we track every quarter, and we actually present to Intel so that they can work on the top bugs and issues that is inhibiting these applications from moving forward. Couple of examples of performance. OpenMC, it's a Monte Carlo simulation code. It is supported by an ECP project. It is developed at Argonne. They use OpenMP, whether they run on NVIDIA, AMD, or the Intel GPU. You see the performance numbers there. Intel is looking good, otherwise I won't show this to you, right? And so whether it is a single GPU or a single node, where a single node is, it's kind of different. We have 6 GPUs on a node. Polaris, which is the NVIDIA equivalent, has 4 GPUs on a node, and Frontier is different too. But they have measured it, and you can see that the higher the bar, the form is, the better it is, and the performance is very good on PVC. So this is one example. Another example is XGC, which is an plasma physics code using for fusion reaction. Again, you see that they are measured on Sunspot, Polaris, and Frontier, and I think higher means better, and they are doing very well. They have also done scaling studies on Sunspot and run to a number of nodes, something like close to 92 nodes or something like that, and it performs very well. And XGC is a C++ code, and it uses a Cocos backend, unlike the previous one, OpenMC, which is all OpenMC. So it uses a Cocos backend for all 3 architectures. The Cocos on Aurora would have a SYCL backend. Cocos on NVIDIA would have a CUDA backend, and Cocos on AMD would have a HIP backend. This is HACK, which is an n-body problem cosmology code. Again, it does very well on Aurora, and or as well on other systems too. We have tested. They have a SYCL version on Intel GPUs, and CUDA version on NVIDIA, and a HIP version on AMD. So some people have chosen to support all 3 programming models on the different GPUs. NWChemX, electronic structure code, chemistry code with different types of physics. Here, smaller means better. So PVC again is doing very well. This is a very interesting application that I'm sharing with you, because they do have a CUDA version, a HIP version, and a SYCL version, but they also have a SYCL version. They have tried their SYCL version on NVIDIA, and they have tried their SYCL version on AMD. And that SYCL version actually performs as well as their native language CUDA and HIP. There was a birds of feather presentation in the recent ECP annual meeting. They also shared it on HPC Wire, so you should read that article. So a fine example that an open standard like SYCL performs very well on these architectures too. So that's good news. And finally, NAMD, the molecular dynamics code. Here you see that PVC performs as well as the other architectures. But some of the loss in performance also has to do with the host CPU. There's a lot of data transfer that happens between the host CPU to the GPUs, and that depends upon the bandwidth and latency. And so because of the difference in the CPUs used, I think the rest of them use an AMD Milan CPU or AMD, the one before Milan Rome CPU, while the Aurora one has SPR. That's all I had. Sorry, I had to go through it fast. There were a lot of slides, but if you have any questions, I'll take them. If you have.
So let's start. Kalyan.
Thank you.
Okay,
Go ahead.
please be loud, little bit louder. Yeah.
Is it possible to use, so you said there is no PCL report. Is it possible to use API or API relationship here?
Yes, they do support it. I do not know. And if you're asking about Intel GPUs, they are supported, but we are encouraging people to use SYCL and things like that. I don't know how long they.
Device. Yeah. Will it work?
Yeah, it will.
Can I get a device monitor out?
Yes, yes, yes. Yes, there are codes that are using it. And I'll send you examples.
My name is Simon from Tokyo. Single slingshot
Next,
network. So
yeah.
how do you get from MPI or the HPE?
I hope Keith Underwood, wherever he
Yeah,
is.
it's there on the.
Oh, okay, okay. I hope Keith will talk about that on it. Yes, yes. So it is, so the ratios are not perfect. You have 6 GPUs, 2 CPUs, and 8 NICs. So it provides a job for a performance engineer, and so they can keep working on it. Yeah. But we do have examples in our documentation as to what the best ratio is and how do you schedule jobs. Most of the jobs that we have wanted to use one MPI rack with 1 GPU. And the mix also, even though you don't have to, you can use collective, all the 4 NICs are connected to 3 GPUs and the other 4 NICs are connected to the GPUs. So you use the collective bandwidth too. Yeah.
Also, PVC direct slingshot.
Yes, yes. The GPUs are, you can data transfer from the GPU memory. Yeah. And the MPI has optimizations for that. One of the optimizations I listed in that was for intranode optimizations to do exactly that. Yeah.
Any more question? We can handle one more. Okay, so if not, let's again thank Kalyan.
Thank you.
So we'll move to the second talk of the workshop.